Hello everyone and welcome back. My name is Mr. Cobalt, and in this video we're going to go over valence bond theory and how it's applied to multiple bonds in molecules. So let's get into this. So we're going to kind of go over a few examples and use those examples to try to explain how we're using valence bond theory to explain how we get to these different kinds of bonds. And so the first example is going to be C2H4. And so that's acetylene. And so the first thing we want to talk about is with regard to valence bond theory. Valence bond theory assumes that the bonding occurs locally, that the electrons and the orbitals are localized to particular atoms. And then there's overlapping of the orbitals, these atomic orbitals that have electrons, and they pair up. So one electron in one localized orbital on an atom will pair up with another electron in an orbital on another atom, and that they pair up, and that forms the bond. So there's this idea of localized bonds, whereas with molecular orbital theory, bonds aren't so localized. Electrons aren't so localized in a lot of respects. But we won't get into molecular orbital theory in this video. We're going to stick to valence bond theory. Another thing to remind ourselves is we're going to talk about the hybridization of orbitals to create hybrid orbitals, right? So again, we're taking this is the idea where we are taking and we are adding together mathematically atomic orbitals in order to create what we call hybrid orbitals on the atom. And so we'll talk about that. Okay, so let's get into our example. So here we have C2H4. And so here is the Lewis dot structure. And one of the things we know about this experimentally is that the structure or the shape or the angle, this HCH angle here, and the HCH angle here is 120 degrees, or about close to 120 degrees. So this is going to indicate that the carbons are sp2 hybridized, meaning that you took an s orbital and two p orbitals and hybridizing them together. And when we mean hybridizing, we mean combining them mathematically to produce equal energy hybrid orbitals. So we're going to take orbitals that are close in energy but are not identical in energy, and then we're going to add those and combine them together to get the same number of orbitals, but now they're equal energy. So if we take an s and two p's, that's three atomic orbitals that have different energies, right? So the s is different from the two p's. You're going to then combine those, and then you're going to get three equal energy sp2 hybrid orbitals. And so that is part of valence bond theory. So one thing I want to start off with is the idea of hybridization. So the carbons here are going to be sp2 hybridized because, again, the idea is that we know experimentally that the angles are 120 degrees. That indicates that it's going to be trigonal planar, and sp2 hybridization is tied to the trigonal planar shape. And so if we're talking about hybridization, here we have our typical carbon atom. Carbon atom has 4 valence electrons. So it's got the 2s and the 2p. So it's got one 2s orbital and 3 2p orbitals. And so because it's in group 4, it has 4 valence electrons. And so if we're in the ground state, then the 2 electrons, the lower s2, the 2s orbital here, well, it's going to be filled with 2 electrons. And then the next 2 electrons are going to fill the 2p orbitals. And again, according to Hund's rule, you're only going to fill in one at a time with 1 electron with the same spin. According to Aufbau principle, we're going to fill in the energy orbitals from low energy to high energy. And so if we're in the ground state, meaning that we don't have any excited electrons, all the electrons are in the lowest energy orbitals possible, then this is what you get. Now, during the hybridization process, one of the things we need are single electrons. So according to this, if we look at this, we only have 2 unpaired electrons. So then carbon should only bond twice. But we know that carbon can bond 3 times, it can bond 4 times. It really loves to bond 4 times. That can't be explained from this. So what can explain it is if we promote one of the valence electrons from a lower energy level to a higher energy level. You'll notice here that we have a empty p orbital. So if we could promote one of these electrons in the 2s up to the 2p here, this empty orbital, then we could have 4 unpaired electrons. So we do that. And so now you have 4 unpaired electrons. So carbon can bond 4 times. But now the thing we want to do here is do the hybridization. So here we're going to do the sp2 hybridization, which means that we're going to take the s orbital electron, right? And we're going to take the 2 p orbitals with their electrons, and we're going to add them together, and we're going to get 3 equal energy sp2 hybrid orbitals. So you'll notice that the hybrid orbitals are going to be higher in energy than the s, but lower in energy than the p, because again, we're adding these orbitals together. And so the lower energy s orbital is going to be combined with the 2 higher energy p orbitals. And what you get is 3 equal energy orbitals that are between the s and the p. So they're higher here. And so now you'll see that the 4 electrons, single electrons, are occupying the 3 equal energy sp2 hybrid orbitals, and you have 1 in the unhybridized p orbital. So you have 1 unhybridized p orbital left, and that's going to be important to remember. And this is true for both carbons because both carbons are sp2 hybridized. So this is what is going on. This is what we have at each of the carbons. So now that we have the hybridization, we can now show the sigma bonding and the pi bonding. So here we have, in our Lewis structure, we have a bond between hydrogen and carbon. We have 4 of those. And so you can see here that we are forming sigma bonding here. Sigma bonding is where you get the overlap of the hybrid orbitals along the internuclear axis. What do I mean by internuclear axis? That's the axis that falls right between the 2 atoms, internuclear. So let me fix my picture here. So if you got overlap right between, in that space between the 2 atoms, that is a sigma bond. And so here you have an unhybridized s orbital of the hydrogen overlapping with the hybrid orbitals. Notice we have 3 sp2 hybrid orbitals, right? So here we have the 3 lobes. So each of these is going to be involved in sigma bonding. And you'll notice again we have the trigonal planar shape here for each of these carbons. And so here we have 1 electron paired up with another electron. So we have 1 electron in the s orbital on the hydrogen pairing up with 1 of the electrons in the carbon. So one of these electrons is going to pair up with the hydrogen electron here. And then you got the same thing going on with this hydrogen here. So this 1s orbital of this hydrogen has an electron in it. That's going to pair up with one of the electrons in one of the other sp2 hybridized orbitals on this carbon. And the same thing goes on over here. So you have the hydrogen, the 1s orbital, overlapping with the sp2 hybrid orbital on the carbon. The electrons, the single electrons, are going to pair up, spin down, spin up. Notice they have opposite spins. So this has spin down, spin up. So this is going to overlap and form a bond. So these electrons are going to pair up. And you can see that here and here. And again, here you have one electron in the sp2 hybrid orbital on this carbon. That's going to pair up or overlap with the hybrid orbital, the sp2 hybrid orbital on this carbon here. And so you're going to form a sigma bond here. So you have 1, 2, 3, 4, 5 sigma bonds. And so that means that the total number, remember the total number of valence electrons in this whole molecule comes from the carbons and the hydrogens. We have 2 carbons. So each carbon has 4 valence electrons, so that's going to be 8 total there. And we have 4 hydrogens. Each hydrogen has 1 valence electron, so that's going to be 4 from the hydrogen. 8 and 4 is 12. And so for the sigma bonding, we used 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. That means we have 2 electrons left over. Okay, and so those 2 electrons are then going to be in the unhybridized p orbital. So notice here we have 1 unpaired electron in the unhybridized p orbital. Both carbons have an unhybridized p orbital, right? So here you can see the 1, 2, 3 unpaired electrons here in the sp2 hybrid orbitals, but we also have the 1 electron that's not being shown in the unhybridized p orbital. We're not showing the unhybridized p orbital here, so we have to go over here to show the unhybridized p orbital. And so here we have our structure flat like this. So you'll see that the 2 hydrogens and the carbon here are in the same plane as this one here. And so this is going this way, so it's perpendicular to the board. And then this is the PZ unhybridized p orbital. It is by convention that the z-axis is perpendicular to the plane of the molecule. So if we have the plane here, this trigonal planar part of the molecule here, then the PZ unhybridized orbital is what is perpendicular. We're going to call that the PZ orbital. Okay, so what happens here is, since this carbon has an unhybridized p orbital perpendicular to the axis, or perpendicular to the plane of the molecule, it has 1 electron in it. And then this carbon also has an unhybridized p orbital perpendicular to the plane, and it has 1 electron in it. And those electrons can pair up to form a bond. And so what we have here is the top and the bottom, the lobes of the unhybridized p orbital. And they're different colors mainly because to kind of show that the orbitals are indicated or are basically wave functions, right? So the electrons travel in waves, and so we understand this as a wave function. And so you can have negative and positive overlap and things like that. And so here you have a different color. here as well as here. So here it's orange. And so these lobes here are going to overlap because they're the same kind of sign for the wave. And here we have, these are going to overlap down here. And so this is not in the internuclear axis or space. These are not internuclear. So here we have the sigma bond, right? That's directly along the axis right between the two carbon atoms. But these are outside of the axis, and they overlap and form electron density on the top as well as the bottom, and we call that a pi bond. So sigma bonds are along the internuclear axes. The pi bonds are going to be formed by the overlap of unhybridized p orbitals outside the axis, the internuclear axis. And so you can see here with the sigma bond, we have one bond, and then we have the second bond here called the pi bond. So we have one pi bond and we have one sigma bond. That's a double bond, and that fits the Lewis dot structure, which also fits the experimental evidence. This bond here between the carbons in the acetylene is a shorter bond than what you would expect in a related molecule known as ethane. So ethane is C2H6. It has 6 hydrogens, so it would look, the Lewis dot structure would look something like this. So you have hydrogens on this carbon, 3 of them. This carbon has 3 hydrogens as well. And so this has a single bond between the two. This has a double bond. And so when we look at the experimental evidence, we see that the bond in this molecule is shorter than in this molecule. So this has a shorter bond. It has a stronger bond. The bond energy is much greater between these two carbons in this molecule than in this molecule. So all of this supports the fact that we have 2 bonds between the 2 carbons. One is a sigma bond due to the overlap of the 2 hybridized orbitals, the sp2 hybridized orbitals, and another one due to the overlap of the unhybridized p orbital that have that are singly occupied by valence electrons. And so this is how we can explain the bonding of multiple bonds in a molecule due to valence bond theory. So the next one I'm going to talk about is acetylene. So that has a triple bond in it. So stay tuned. I'll be back with that. Okay, here we are back again. So this time we have C2H2. This is also known as acetylene. I think I was saying acetylene before. The previous molecule, C2H4, that's ethylene. I think I was saying acetylene. Ethylene, or another way of naming this is ethene. So ethene, and then you have C2H6, that's ethane, and then this is also known as ethine. So ethine, ethene, and ethane, right? This is also known as acetylene, right? So we're going to talk about acetylene or ethine right now. C2H2. So this is the Lewis dot structure for C2H2. You'll notice it has a triple bond. The experimentation shows that this is linear. And so we're going to explain that again by valence bond theory. So again, going back to our carbon atoms that are bonded together If it's linear, that's going to indicate that we have sp hybridization because that's associated with a linear shape or a bond angle of 180 degrees, right? Which is what we see from experimentation. And so that means that we would take the s orbital and one p orbital and hybridize those together to get two hybrid hybrid sp orbitals. So again, we start with the carbon that has a ground state. So all of the electrons, the valence electrons, are in the lowest energy levels possible. And so we're going to promote, again, one of the electrons to the empty p orbital. So now we got our three unpaired electrons. And so then we're going to take the s orbital and one of the p orbitals. We're going to hybridize those together. We're going to mathematically combine those, and we're going to get two equal energy sp hybrid orbitals. So that's what we have here. Again, notice that the sp hybrid orbitals are higher in energy than the s orbital was, but are lower in energy than the p orbitals. So lower in energy than the p orbitals, but higher than the s orbital from which it came. Okay, so now again we have our four unpaired electrons, but now we have two of the unpaired electrons in the two equal energy sp hybrid orbitals, and we have two. This time we have two unhybridized p orbitals. Last time we had one unhybridized p orbital. This time we have two. And this is the same for each carbon. So both carbons are going to have two sp hybridized orbitals and two unhybridized p orbitals. So when we show the sigma bonding again we have our two carbons. They're going to have two sp hybrid orbitals, 1 and 2. And this has two sp hybrid orbitals, 1 and 2. And then each of the orbitals, again, has one electron each, right? So we have one electron each. And so this hydrogen here, the hydrogen that's in our molecule here, is bonded to the carbon, and that bonding occurs from the overlap of the unhybridized 1s orbital of the hydrogen and the sp hybrid orbital of this carbon here. And they both have they're both singly occupied with one electron. That's redundant. They both have one electron. They're going to pair up, and that's going to form the bond there. Then we have the same thing happening over here. This hydrogen over here with the 1s orbital is going to form a bond with this carbon here. Again, we have one sp hybrid orbital here and one sp hybrid orbital here. So here we're going to get the overlap of the 1s with the sp hybrid orbital. That's going to form a bond. We got the two single electrons. Those are going to pair up and form a bond here. So that's going to form your bond. And then the bond between the carbons is due to the overlap of the two sp hybrid orbitals. And again, we got one electron, that's going to pair up, and you're going to share the two electrons. That's forming the bond. And all of these are sigma bonds, right? Again, because the sigma bond forms between the internuclear axis here, on the axis between the two atoms, here and here, here and here. Let me fix that again. Okay. So as mentioned before, we have two unhybridized p orbitals, both of which have a single electron. And that is for both carbons, not shown here. So we're going to go over here. And so here we have the sigma bonds in lines here. And we have now the p orbitals. And again, this is one p orbital. This is the pz, right? This is the pz that is perpendicular to the molecule here. But then the other p orbital that's unhybridized is also perpendicular to the z. So this might be the py, right? So maybe the py is unhybridized. So going in order from x, y, and z, x was hybridized, leaving y and z behind. And so here, let me just point this out. So here going up and down, we have orange and blue, orange and blue. So this would be your PZ going up and down. And so you got that overlap here. Oh, I forgot the electrons. So here you have spin up, here you have spin down. And then in this orbital here, on this electron, let's say we have here, this is going to be spin up here and spin down there. So we have this orbital here that has one electron in it. We have this unhybridized p orbital here that has an electron in it. This is going to pair up and these are going to overlap. So we're going to get our electron density overlapping here and the blue on the bottom here. So that's going to be one pi bond. And then we have the other unhybridized p orbital. So we have the blue and the orange here. So this would be like left and right. So this is on the right and this is on the left if we're facing this way, or this is coming on the outside of the board. This is the blue is going on the inside of the board. So that's another way to look at it. And so the overlap of the orbital lobe here on this side of the molecule, and then you got the overlap of the blue on this side. So then you got another p orbital here. I'm sorry, another pi bond here. So you got two pi bonds in this case. You've got the up and down pi bonds, and then you got the left and right, the outside, inside pi bond here. So that's giving you two pi bonds because you have two unhybridized orbitals that each contain a single electron. Those are going to pair up between the carbons. And so that is going to be in addition to the sigma bond here. So you got three bonds. You got one sigma bond and you've got two pi bonds, matching what we know here from our experimentation, from what we know from the experiments. And this also fits with the data, right? Given the fact that we know that from experimentation, the bond between the two carbons in the ethine molecule is shorter than that found in the ethane with the single bond and ethene with the double bond, right? Which is what we would expect. Right, that would be if we have triple bond character, we would expect that the bond be shorter. Also, we know that the bond energy is much higher compared to that of the the double and single bond in the ethene and ethane respectively. So again, this is how we would explain the multiple bonds, double and triple bonds and single bonds, and is by the overlapping of different bonds, hybrid and unhybrid as well. And so I hope this helps clarify how you can use valence bond theory to explain multiple bonds in molecules. So the next thing I want to talk about is labeling of the bonds in valence bond theory. So I'll be right back. Okay, so let's talk about how we label the bonds according to valence bond theory. So we're going to use both the symmetry as well as the orbitals involved in the bonding. What do I mean by symmetry? I mean simply sigma or pi. Sigma, again, is referring to bonds that are along the internuclear axis, that overlap along the axis. And then which is going to be either hybrid orbitals overlapping with unhybridized orbitals like s orbitals. And then you have your pi bonds that are outside of the internuclear axis between the atoms, and those are normally going to be unhybridized p orbitals overlapping with each other. Okay, so here using this example of our ethyne molecule C2H2, here we have an overlap of the unhybridized s orbital with the sp hybrid orbital of the carbon, and this is a sigma. So the way we would label this bond here between the hydrogen and the carbon would be with the sigma symbol. And then what we do is we put the carbon, right? We're putting carbon down as well as the hydrogen. And so after we write the carbon, we're going to write the hybridization of the orbital, or what orbital are we dealing with the carbon in the overlap or in the bond. And so in this case, we would have sp. So this would be a sp orbital from the carbon overlapping with the hydrogen. And then we would put the orbital that's involved there, which is the 1s. So we put 1s. And so that is labeling this bond here. It's a sigma, and the orbitals that are overlapping is the sp hybrid orbital of the carbon with the unhybridized s orbital of the hydrogen. So this is the way you would label the bond here. Now the bond between the carbons, there's two bonds there. And so the way you would label that is, again, you'd have the sigma bond. So you have sigma, that's the symmetry, right, along the internuclear axis. And then what are the atoms involved? It's carbon and carbon and the sp orbital, the sp hybridized orbital. So it'd be carbon, sp orbital bonded to carbon, sp orbital. And then you also have the two hybrid or two pi bonds, right? So the pi bond, it would be pi, right? And so since we have two pi bonds, you would have to indicate the two, the two unhybridized p orbitals. But, I guess you probably don't have to. But you could label it px or pz and py, but I'll just show you with just a generic. So we have the carbon, and since the orbital involved here for the pi bond is just an unhybridized p orbital, and then for the other carbon it's the same, so it's the carbon, and then the orbital involved there, which is again p. So giving you the pi bond between the two carbons is the unhybridized p orbital overlapping with an unhybridized p orbital on both of the carbons. And so this is the way you would label the bonds in your molecule according to valence bond theory. So ladies and gentlemen, that is it for the video. I hope you enjoyed the video. I hope this really helped to clarify how valence bond theory can be used to explain and portray the bonds that are involved in molecules with multiple bonds, single, double, and triple bonds. And so again, I showed between carbon and hydrogen and carbon, but you can do this with bonds between carbon and oxygen and nitrogen and all that, any double and triple bonds that you run into. So that's it for this video. If you enjoyed this video, if this video helped you in any way, then please like the video, share the video, hit that like button somewhere around here. Also, make sure that you subscribe to my channel. Help me out here. Also, when you do that, click on the little notification bell. And when you do that, make sure you click all so you can be notified by all the videos I put out. And finally, put a comment down below in the comment section. Let me know what you think. Ask me questions. I would love to hear from you. If you have a question or a problem you need help with, or if you have a topic you would like me to cover, put that down below. Help me out. I would love to do that for you. Thanks for joining me, and have a great day.